In 2016, a team of astronomers led by Christopher Consolis at the University of Nottingham did something that sounds almost mundane when you first hear it. They counted galaxies, and in doing so, they rewrote one of the most fundamental numbers in all of science. The previous estimate, the one that had been sitting in textbooks since the Hubble Space Telescope gave us our first deep look at the universe in the mid-1990s, was around 200 billion galaxies in the observable universe. That number had been accepted for roughly 2 decades. It felt settled. It felt real. Consolis and his team looked at those same Hubble Deep Field images, added data from other telescopes, built 3-dimensional maps of galaxy density across cosmic time, and then applied mathematical models to account for all the galaxies too faint and too small and too far away for any existing telescope to actually see. And the new number they arrived at was not 210 billion. It was not even 300 billion. It was 2 trillion, not 10% higher, not twice as high, 10 times higher. In a single study, the number of galaxies in the observable universe increased by a factor of 10. And right now, according to that same research, roughly 90% of those 2 trillion galaxies are too dim and too distant for even our best telescopes to detect. We are living inside the grandest structure in existence, and we can only see 1/10 of it. That number should bother you more than it probably does. So let us try to actually feel how large 2 trillion is, because the brain does not naturally process quantities at this scale. It just rounds up to the word enormous and moves on. That is not good enough here. Start with something manageable. Count to 10. That took about 3 seconds. To count to 1,000,000 at that pace would take roughly 35 days. To count to 1 billion would take nearly a century. And 2 trillion is 2 million millions. To count to 2 trillion, one number per second, without sleeping, without stopping, would take approximately 63,000 years. The last time a human would have reached the number you are at right now, Neanderthals were still walking the Earth. That is a galaxy for every second of the last 63,000 years. And each of those galaxies contains, on average, somewhere between 100 billion and several hundred billion stars of their own. There are more stars in the observable universe than there are grains of sand on every beach and every desert on Earth. You have probably heard that comparison before. The number is so large that it stops meaning anything. But here is the thing that should stop you entirely. We are not talking about stars. We are talking about entire star systems, entire galaxies, entire islands of hundreds of billions of suns, and there are 2 trillion of them. The scale is not just large. The scale is genuinely outside the range of human intuition. Now here is the part that most coverage of this study glossed over. The 2 trillion number is not the total count of galaxies that exist right now. It is the number that have existed in the observable universe across the entirety of cosmic time. Because early in the universe's history, when it was just a few billion years old, there were enormous numbers of small, faint dwarf galaxies that have since merged together into larger ones. Consolis's team recovered those ancient populations, not new galaxies that formed somewhere else, the fossil record of galaxies that were later consumed, absorbed, merged out of existence. The universe began with more galaxies than it has now. They have been cannibalizing each other for 13 billion years. What we see today is what survived after 90% of the original population was swallowed. The night sky looks empty. Even on the clearest night, the overwhelming impression is of darkness. And yet the observable universe is not dark. It is full. Every direction you look contains thousands of galaxies beyond the stars visible to your eye. The apparent emptiness of the sky is an artifact of your biology, not a description of what is actually there. This connects to one of the oldest puzzles in astronomy, something called Olber's paradox. If the universe contains an effectively enormous number of stars spread across all directions, why is the sky dark at night? Every line of sight should eventually terminate at a stellar surface. The sky should blaze with light. The fact that it does not confuse scientists for centuries. The resolution is deeply connected to the age and expansion of the universe. The universe had a beginning. Light from the most distant galaxies has not had infinite time to reach us. And the expansion of space stretches that light into longer wavelengths, shifting it beyond what our eyes can detect. The darkness of the night sky is a cosmological fact about time. It is not emptiness. It is the edge of how far light has traveled since everything began. Now, if 2 trillion galaxies is already a number your brain is struggling with, the structure those galaxies actually inhabit is something else entirely. At the largest scales, the universe does not look like a uniform distribution of randomly scattered galaxies. It looks like a web. Specifically, it looks like the largest and most intricate web imaginable, a structure formerly called the cosmic web. And the word web is not a casual metaphor. Here is how it formed. After the Big Bang, the universe was not perfectly uniform. There were tiny fluctuations in density, quantum-level variations in how matter was distributed, stretched to cosmic scale by the rapid expansion of the early universe. Those slight overdensities pulled in surrounding material through gravity. Over hundreds of millions of years, gas flowed along those gradients, condensing into sheets, then into elongated filaments, then into dense knots at the intersections of those filaments. That is where galaxies formed, not randomly scattered, but organized along a scaffolding of dark matter that gravity had already assembled. The result is that the observable universe, when mapped, looks like an enormous three-dimensional network of bright strands and dark voids. The filaments are highways of matter, stretching hundreds of millions of light-years. The nodes where they intersect are galaxy clusters containing thousands of galaxies bound together by gravity. And between the filaments are voids, regions of near-complete emptiness that can themselves span hundreds of millions of light-years across. Here is the number that reframes the whole picture. About 80% of the volume of the observable universe is void, empty, essentially nothing. Most of the universe, by volume, is not where the galaxies are. It is the dark space between the web strands. The 2 trillion galaxies occupy the remaining fraction, packed along filaments and concentrated at nodes, a thin luminous net stretched across an overwhelming darkness. The Bootes void, one of the largest known voids, is about 330 million light-years across and contains almost nothing. If you lived in a galaxy at its center, you would look outward in every direction and see essentially darkness. The luminous web surrounding you would be so far away it would be invisible to any naked eye. The cosmic web from inside a void would be a horizon you could never reach. And here is where something genuinely strange enters the picture. In 2020, astrophysicist Franco Vatsa at the University of Bologna and neuroscientist Alberto Folletti at the University of Verona published a paper directly comparing the structure of the cosmic web to the structure of the human brain. Specifically to the cerebellum, the region responsible for motor coordination. The comparison had been made informally for years. Put an image of a slice of the cosmic web next to an image of a neural network, and they look startlingly similar. Dense nodes, thin connecting filaments, large empty regions between them. The visual resemblance is immediate. But Vatsa and Folletti went beyond the visual. They applied the same quantitative tools cosmologists use on galaxy distributions to neural networks. They measured how complexity and clustering vary across different spatial scales in both systems. The human cerebellum has roughly 69 billion neurons. The observable cosmic web contains hundreds of billions of galaxies. The numbers are already in the same order of magnitude. More than that, the structural complexity of the two networks, measured using identical mathematical frameworks, turned out to be remarkably similar. Two systems separated in physical size by 27 orders of magnitude, that is, a billion times different in scale, showing comparable degrees of self-organization. This does not mean the universe is conscious. It does not mean the cosmic web is thinking. The physical processes that produce neural networks and the physical processes that produce the cosmic web are completely different. One is electrochemistry. The other is gravity and dark matter. What the comparison reveals is something subtler and more important. It reveals that certain organizational principles, the way complex networks distribute material through available space and balance connection against cost, produce similar geometric outcomes regardless of the underlying physics. Gravity and synaptic development both arrive at filaments and nodes and voids because those configurations represent efficient solutions to a shared structural problem. The universe is not like a brain because it is made of the same stuff. It is like a brain because when matter organizes itself at scale, it tends toward webs. And that pattern keeps appearing everywhere complexity assembles itself. Now, whether the universe is asking itself a question or not, the numbers it presents do raise one that human beings have been unable to put down for a very long time. If the observable universe contains 2 trillion galaxies, and each of those galaxies contains hundreds of billions of stars, and if a reasonable fraction of those stars host planets with the right conditions for chemistry of sufficient complexity, then the question of whether life exists elsewhere in the universe shifts character entirely. It is no longer a question about possibility. It becomes a question about whether absence everywhere else is even numerically coherent. For that many stars across that many galaxies, across that much time to all produce the same outcome, nothing would require something going wrong at every step across a number of chances large enough to dwarf any intuition we have. The scientifically careful position is that we do not know. We have one confirmed data point for life, ourselves. And extrapolating from a sample size of 1 is exactly the kind of reasoning careful science resists. The conditions for life may be far more specific and far rarer than raw numbers suggest. But the universe is no longer the modest collection of stars visible on a clear night. And the 2 trillion makes the question genuinely hard to close. Here is what makes this moment unusual. We are the first generation of human beings with instruments capable of beginning to see the actual scale of what exists. Every culture before ours built their picture of the universe from what unaided eyes could resolve. A few thousand stars, the smear of the Milky Way. No sense at all of the web behind it. In 1924, Edwin Hubble proved that the fuzzy spiral nebulae people had been cataloging were not clouds inside our galaxy, but entire separate galaxies, millions of light years away. The universe went, in the span of one astronomer's lifetime, from being essentially just the Milky Way to being a collection of billions of galaxies. That was one of the most violent revisions in the history of human thought, and it happened quietly, through journal papers and telescope reports, without a cultural moment anywhere close to matching the scale of the discovery. The 2016 revision from 200 billion to 2 trillion was the same thing happening again. Another order of magnitude added to the size of the universe in a single paper. And the cosmic web, the structure those 2 trillion galaxies actually inhabit, adds another layer to that revision, because mapping it reveals that the distribution of matter across the observable universe is not random, not uniform, not chaotic. It is organized, structured, patterned in a way that mirrors organizational principles we find inside the most complex objects we know of in the biological world. What we do not yet have is a conceptual vocabulary adequate to what that means. We have the map, we have the number, we have the mathematics that explains how the web forms. What we do not have is a framework for asking what kind of thing the web is. Whether the pattern repeats at scales beyond our observational horizon, whether the filaments and voids and nodes are the largest structure in existence, or whether they are themselves embedded in something larger that we cannot yet see. The observable universe is not the universe. It is the portion visible from our location at this moment in cosmic time, given the finite speed of light and the finite age of everything. Beyond its edge, the same physics applies. The same dark matter assembles the same webs. The same galaxies cluster at the same intersections. And there is almost certainly far more of it than we will ever be able to access. 2 trillion galaxies, organized into a web that mirrors the architecture of a human brain, spread across 93 billion light-years of observable space, which is itself a small window cut into a universe whose total size we cannot measure. That is what we are living inside of. Not a quiet corner of empty space, a single node in the largest web there is. If you found this one worth your time, hitting like genuinely helps this channel reach more people who would appreciate it. Subscribe if you want to be here for the next one, because we are going to talk about what the James Webb Space Telescope found at the very edge of the observable universe. Galaxies that formed so quickly after the Big Bang, so large, so bright, so soon after everything began that according to every model we had, they simply should not exist.